Yeah. Okay. So any questions, comments? Okay. So last time we had some sort of a motivating discussion of, or about what high-dimensional statistics is, and I'm not going to repeat that, but we'll come back to the problem, basically the problem of sparse regression, after we have some basic sort of tools in the form of concentration inequalities to attack the problem. So so this is going to take a while, but as I mentioned, they're very useful, and the more you go over them, even if you've seen some of it, it's good to get comfortable with these ideas. And there are many variations. Some of them I'm going to post on as homeworks and such. But this particular version that I'm going to let's say discuss is I would say is more recent way of looking at things. So the classes of random variables that we're going to consider, I mean, they have been known, but it's just more recent way of thinking about concentration. So so these ideas that we went over last time are pretty classical. So the main tool in dealing with these concentration inequality is basically a variation of this Markov inequality, which holds for a non-negative random variable. And if you have a non-negative random variable, this always holds. We did the proof, even if the expectation is not finite. Okay, this side will be infinite. It's a useless inequality, but there's no assumptions basically other than x being non-negative. And you can see that if it's finite, it gives you some form of a decay of the tail. The tail has at least has to go like 1/t. But then if that's all you're going to assume that the expectation is finite, this is how far you can get. There are distributions for which the tail just exactly drops like 1/t. If you assume the second moment exists, so this sort of implies that the mass is more concentrated. Okay, so the tails can't go too slowly, otherwise this would be infinite. So this imposes this second order tail decay. It's like quadratic, which is called the Chebyshev inequality, and it's just a direct consequence of this applied to deviation squared, for which you get the variance here. And then if you have the kth moment, absolute moment, finite, this implies more concentration. Okay, so again, hopefully, I mean, everyone sees that this is again a direct consequence of this. But the interesting point is that the tails now decay like 1/t to the k, and if you have all moments, okay, so you have all these inequalities, it means that the tails are decaying faster than any polynomial. Okay, then you might think, oh, maybe they're decaying exponentially, and that's sort of where we're going. So, any question about this? Okay, so here's a motivating, not motivating, but here's like an attempt to get exponential tails. Suppose we have Bernoulli random variables with probability 1/2 of coming up like 0 or 1. They're IID, and you form the sum. Central limit theorem gives you the distribution of this rescaled sum. Okay, so this quantity here is the mean of Sn, right? And this here is what? N/4 is the variance of Sn, right? So the variance of Sn is in general n times p times 1 minus p. P is the probability here, right? Just recall, if this is p, variance of Bernoulli is p times 1 minus p. Variance of the sum, because they're independent, is going to be the sum of the variances, which gives me n times p 1 minus p. P is 1/2, so you get n/4. And so root of this is just the standard deviation of the sum. So I'm standardizing. Subtract the mean, divide by the standard deviation. This conversion distribution to a normal, it means 0 and 1. That's the CLT. Okay. So if you unpack this definition, or the definition of convergence distribution, it tells you that basically the probability that Zn, let's say, is bigger than t, converges for every t to the probability that the Gaussian, standard Gaussian, which is this g here, bigger than or equal to t for all t. Say for all t. We're going to do t bigger than 0 by holds for all t. And if you rearrange, so plug in Zn, right, and then rearrange, you get what I have here. Okay, it's just exactly the same event. And so it goes to this, let's say for large n, we can say it's approximately this. And this is easy to show that if t is bigger than or equal to 0, this inequality holds. So you have to just do some integration. But the tails of a Gaussian are well known to satisfy this exponential decay. Okay. This seems all good, right? So you achieve that this is less than or equal to, roughly less than or equal to this. And if I reparameterize, let's say t equal alpha root n, if you plug in t alpha root n is basically the scale of the standard deviation of Sn. So if I move a little bit in that direction, this simplifies to this. So what this is saying is that n over 2 is the mean. If I move away from the mean by a factor of alpha, if you go up above, then the probability drops like e to the negative n times alpha squared. So I'm replacing t with alpha n, so you get an n here. So that's like the exponential concentration that you look for. As the sample size grows, this drops exponentially fast in n. There's a factor alpha here, which is unavoidable. You can't set it equal to 0, but if I set it equal to something other than 0, this is going to be, let's say, constant. I can say that Sn is bigger than, let's say, n over 2 times 1.01, with probability like minus n. Let's say if I take it, let's say just do 1.1, this would be n to the 200. So eventually, although it's a big constant, n is going to dominate, and this goes to 0 very fast. Something like that, okay? This is all good, except that there's this approximation here. Right? So far, so good. And unfortunately, this approximation, the error in this approximation is bigger, much bigger than this side. So although we have something that looks good, the difference between this and this is much bigger than this. This is exponential in n. And you can show that the error in CLT, basically, the deviation uniformly in t is bounded by rho divided by root n, and rho is, I believe there's a constant. I always miss this. It's not exactly this, but there's a constant here, and people keep improving it. You can check what is the best constant for Bayesian at the moment, and it's not big, but there's a constant. That rho is like the normalized third moment, central third moment. So depending on the third moments of the distribution, this is a constant, and then drops like 1 over root n. Okay, so and then you can show that this bound is tight, so that it's not like we can improve this. It's just one bound, and someone might do better. The scale should be like this, and the reason is if you look at the Sn. The probability that this is exactly equal to n over 2, let's say n is even, the probability that this is exactly equal to n over 2 is this. So n choose n over 2, 1 over 2 to the n. right? Just like this is p to the k, 1 minus p to the k and minus k. This is the PDF of a PDF, PMF of this. So if I plug in p equal 1/2, k equal n over 2, you get this, and then using some Stirling's formula approximation, this asymptotically behaves like 1 over root n. Okay, the fact that this equal n over 2 is like that, and this equal n over 2 is 0. Okay, so you can justify for yourself that if I have this, I can just sort of basically find an interval that isolates this, and then let that interval be, the length be as small as I want. I can make this as small as I want, but this is going to be like this. So the error has to be at least 1 over root n. So this cannot be improved. And so we're stuck. So Bernoulli is this is like the best that we can hope for. This like has all the moments, like the most well-behaved distribution, and we can't get it for this. Then like if I have like other distribution with tails, probably things are even worse in terms of the third moments here. But the thing is, this approximation, this side goes to 0 as e to the negative n, but the error, there's an error which is like plus 1 over root n. So that dominates this. So this makes this attempt all like useless, basically. Okay, so you have a very nice bound, but it's just washed out by the error in the approximation. So is this sort of clear? So CLT is interesting, but it's not useful to get such a bound. So what is the solution? The solution is just do it directly. So directly attempt to control this quantity rather than say this converges to Gaussian and then use the Gaussian tail bounds. And the idea is, probably most of you have seen it and know it, is to use the Chernoff bounding technique, or Chernoff's idea, which is basically an application of the Markov, but instead of applying it to the random variable, we apply it to the exponentials of the random variable. So if I have Zn, again, Zn is this standardized, let's say, sum. I want to control its tails. I'm going to raise it to, like, raise an exponential to this power. So multiply by lambda both sides of this. Lambda is positive. And take the exponential. Once I take the exponential of both sides, so this is, exponential is monotone, right? So, and then 1 to 1. So this event is the same as this event, okay? There's nothing lost here. Now I have this inequality. What is this inequality here? Yeah.
Because we use explanation such that if we take the Taylor expression of the exponential that has infinite movement constraint.
Yeah, that's, yeah, so exactly. So if, okay. So maybe you can want to continue, yeah. So
yeah, I mean, because it has so many, it has infinite exponents. So
right. That's the main point. The issue is that this has all that finite set of moments. It's just that the CLT is not strong enough. So CLT holds for, as you probably you want to point out, this holds as long as you have the second moments, right? So once you have the second moments, then this holds. It's just that it's universal for all the distributions that have finite second moments. So you're not hoping that you get better than this, and then also not better than this. But the thing is that we're applying it to something which is more regular, as you point out. Yeah, that's a good point. So we'll come back to why this is. But yeah, this inequality, if it's useful, it means that this has to be finite. And for this to be finite by a Taylor expansion, you'd see that all the moments have to be sort of finite. Okay, so for Chernoff bound to make sense, you would need that this at least be finite for some lambda, right? And That's a great point. Okay. Now, why this is true? Do I have somewhere that? No, unfortunately, we don't have the answer there. So what is that inequality? Sorry? Yes, Markov. So this is a non-negative random variable, always, because of the exponential. So I can apply the Markov. How do I apply the Markov? It's just, if you go back up, this is the Markov inequality, right? So I'm applying it with e to the t like lambda zn. This is e to the lambda t. So what I get is that e to the lambda zn here, e to the lambda t here. Okay. It's just that inequality. And you can see one of the advantages of raising it to, like doing the exponential, is that this is always going to be non-negative. So I don't have to worry about that. And so this is the start of sequence of assumptions. So so it makes sense. Let's point this out. It makes sense if MGF is finite, sort of is equivalent. It's a little bit probably stronger than just implies that all the moments are finite. Okay. So this points out to studying the MGF of random variables. Okay, so depending on how they behave, you might get a different tail bound. So far clear, people? Okay, so this is the thing that I said is usually a more modern viewpoint. So we define different classes of random variables based on the behavior of this MGF. And then their equivalent characterization in terms of their tail behavior. So the first class is the class of subgaussian random variables. So a subgaussian random variable is a zero mean random variable whose MGF satisfies something like this. Okay, so this is bounded by an exponential for all lambda. And this side you can confirm is the MGF of a standard normal with mean zero and variance sigma squared. So if you, MGF is like the moment generating function. That's the, they mention it, moment generating function. So the subgaussian random variable is a random variable whose MGF is upper bounded by the MGF of a Gaussian. In particular, a Gaussian is always subgaussian. The zero mean assumption is, so you can remove it and assume it, and this forces the mean to be zero. You can do a Taylor expansion and see if this holds for all lambda, then expectation of x has to be zero. So if you want, you can remove it. But then what if the random variable is not zero mean? You can just say a general random variable is subgaussian if the centered version is satisfying this. Okay, so we can have subgaussian random variables that have non-zero mean. Some authors assume subgaussianity means zero mean. Again, just watch out. Most people now just recognize that subgaussianity can be general. Okay. So what other examples are there? So a Rademacher random variable or symmetric Bernoulli, that's another way of saying it, is subgaussian. A symmetric Bernoulli is a random variable that takes +1 and -1 with equal probability. Okay. The MGF is just, if you want to compute it, takes two values, x takes two values. So this expectation is 1/2 e to the lambda times 1 plus 1/2 e to the lambda times -1, which is just this cosine hyperbolic of lambda. And then you have this inequality, which I let you verify. It's just an elementary inequality. You can try to do Taylor expansion and such. Okay. Next step is that any bounded random variable is subgaussian. So if the distribution has finite support, or like bounded support, not finite, bounded support, then it's subgaussian. So it includes a lot of random variables. So if x is in A and B, then one holds with the sigma, which is sometimes called a subgaussian parameter, or a subgaussian parameter with this value. So this sigma is not unique. You can think of the smallest sigma that satisfies this and give it a name. We'll do something like that later, but sometimes it's easier to let it be any sigma. So subgaussian parameter is a little bit fluid. So not necessarily the smallest possible, but this is a good one. It's not, you can get it with larger values, let's say b minus a, for example. To get it with this, I guess you have to do a little bit of work. Maybe you'll do it in the homework problems, but it's non-trivial, so you have to do some work here. Okay, so far so good. So this is an exercise, hopefully you'll see in the homework. Okay, so there are other possibilities, but let's have this. This is a sufficiently large class. So you're not defining something which has just two instances. So any bounded random variables, so uniform random variables are like this. Uniform is 0 to 1 and so on. Questions? Okay, so what is the use of this? I can just, for any random variable in this the class, I can plug in this upper bound here, and then I get an immediate upper bound on the tail, right? So if we plug this in there, so we're going to do it for general subgaussian random variables. Forget about the z now. Suppose I have a zero mean subgaussian random variable, which satisfies that moment generating sort of bound, MGF bound. So expectation is bounded by e to the sigma squared lambda squared over 2 for all lambda. Yeah, all lambda in R. Then I'd have this tail bound. So you would get a tail bound which involves the sigma squared, which is the subgaussian parameter. This is not necessarily the variance, okay? Just be careful. And if I have this, I can replace x with negative x. And you can see for a zero mean random variable, because this lambda is in R, if I change x to negative x, I can change lambda to negative lambda and the same bound holds. So random if x is subgaussian, negative x is also subgaussian. If things are zero mean. Even if they're not zero mean, it would be, but you need some other stuff that we talk about to show that. But if it's zero mean, it directly follows from this. So if I do this in this bound, so the exact same bound holds for negative x. If I put negative x here and then rearrange, I get the lower bound for like lower tail. So I have the probability that x bigger than t is like that, and then probably that negative x, which is saying x is less than negative t, is bounded by the same quantity. So oftentimes I can combine them, the same thing. I can combine them by the union bound. So the probability that x is bigger than t or x is less than negative t is bounded by twice e to the negative t squared over 2 sigma squared. Okay, that's a two-sided bound. And this is, if you think a little bit about this, this is just saying that absolute value of x is bigger than t. Okay, so I can, from this, I can immediately get absolute value of x bigger than t, and I put a 2 here. So we often don't do this if it's obvious. So you just show one side of the tail. It's not always this obvious. So the two sides of the tails could be different. So it could be harder to get, for example, lower tail. But for a subgaussian, things are symmetric, sort of. At least if you just want to use this, things are symmetric. Okay, that little excursion there, is it clear to people? So we're going to just follow like try to prove this. And proving this is also kind of almost done. So we have a bound here, right, already. Let me rewrite it. So we have a Chernoff bound, which is probability that x is bigger than or equal to t is less than e to the negative lambda t expectation of e to the lambda x. Okay, and then I have a further upper bound on this by assumption that this is lambda squared sigma squared over 2. Okay, so this gives me the bound e to the negative lambda t plus lambda squared sigma squared over 2. Okay, let me hide the rest. So what should we do at this point? Maybe it's not visible. Let me put it there. Cut page here. Let's do it here. So I have this. So what is the next step? This holds for all t and let's say t bigger than or equal to 0 and lambda in R. Yeah.
What's all you just like take the minimum of all
Great, yeah. So you have a bound which is parameterized in terms of a parameter. This is a free parameter, so you want to push it as down as possible, so you minimize this over lambda. So once you have this bound, you also have that this is bounded by the infimum over lambda in R, I believe. Well, actually, lambda has to be also positive. Anyone remembers why? Because of the Chernoff bound, when I multiply by lambda, I want to keep the sign of the inequality. If lambda is negative, this has to like change. So the subgaussian upper bound is valid for any lambda, but the Chernoff bound requires me to have this. So I can only optimize over lambda bigger than 0, e to the negative lambda t plus lambda squared sigma squared over 2. Okay, that's basically my bound. And then this is just an optimization problem. And E is monotone, so basically you have x infimum of the inside, or let's say minimum of the inside, negative lambda plus lambda squared, sigma squared over 2. You take the derivative, or whatever you want to do. Hopefully this turns out to be negative t squared over 2 sigma squared. Okay, so the minimum, so you find the minimum, it's just a quadratic has a minimum, right? This should be like that. Okay, I'll let you figure out the details. It's just simple enough. Okay? Just minimize this, or maybe let's do it. Because you have to also take into account this constraint. So if I want to minimize this, the easiest way is to take the derivative, negative t plus 2 lambda sigma squared over 2. Set it equal to 0. Lambda has to be negative. Has to be what? A t over sigma squared, actually. That's the optimal lambda. If I plug it in there, I get negative t squared over sigma squared plus t squared sigma squared squared sigma squared over 2. One of them cancel out. And this turns out to be that. So this has a minimum, and the minimum turned out to be carrying at a positive lambda. So So this is well within this range. So we actually can do this, okay? If it turns out that this lambda is negative, then I'm at the boundary, so I have to go with the boundary, and this will come up later. But fortunately, in this case, because let's say if t was negative, then I couldn't do this, right? So this bound only is valid for t bigger than or equal to 0. Otherwise, it's all that there is to it, and we prove this result. Okay, question? Okay, you might think this is not that interesting because this is just one random variable. It doesn't seem like concentration. It does behave like concentration because it's telling you that if you move away like a factor of sigma from 0, then this goes down. So sigma behaves like a measure of concentration, right? So if I let t be alpha times sigma, this is saying that x bigger than alpha sigma is e to the negative alpha squared over 2. I can make this as small as I wish. Let's say if it's 2, this would be e to the negative 2. If it's like 3, it would be e to the negative 9 over 2, like e to the negative 4, which is pretty small, right? So if I go 4 times the subgaussian parameter, that contains a lot of the mass. Okay, but this has a better use, which is to apply to sums of independent subgaussian random variables. Okay, and this is what is key. So fxi's are independent 0 and subgaussian with parameter sigma I. Then the summation is going to be subgaussian with parameter sigma, which is just the root of the sum of the squares of the sigma i's. Okay, that's the key result that makes it interesting. So note that they not have to be like IID. They can be different subgaussian. Subgaussian is a class of distributions, right? They just have to be IID, and each one has a subgaussian parameter. These are also upper bounds. They're not necessarily exact values of the minimum parameter. But this result follows, and it's really easy because they hide the proof. Why is it easy? Unfortunately, you can see probably. Okay. Yeah. Yeah, exactly. So that's the use of MGFs. It just turns the summation into a product. So expectation, that's why they're useful. This is e to the negative lambda summation xi, and this is just expectation of the product e to the lambda xi, and by independence, this is where independence comes in. You move the product outside e to the negative lambda xi, sorry, expectation lambda xi, and then this is bounded, upper bounded by, these are all non-negative, so product e to the lambda sigma I is squared, lambda squared over 2, and then the product goes into the exponent and turns into a sum. Get lambda squared summation I sigma I squared over 2. Okay, and you can see that this is now a new parameter, which we can call it sigma squared, and this shows that this is subgaussian with parameter sigma squared, which is exactly what we have here. Okay. So that's the main use of basically MGFs and the original idea of Chernoff to just do this. So the thing is, if all of them have subgaussian parameter sigma equals sigma, like sigma 0, let's say, then this would be root n sigma 0. So the subgaussian parameter like scales like root n, which is a form of concentration, as you'll see, instead of scaling like n times sigma squared, you're adding n things. The subgaussian parameter just scales as root of the number. It's just like how the variance behaves. So if you add a bunch of independent random variables, the variance scales like n times the variance of each one. The standard deviation scales like root n. That's what causes the concentration. Any questions? Okay, I think this is simple enough. And then immediately this result, if you combine this with this tail bound, I can just apply this tail bound now to this sum. What I would get is that this n right here, and this sigma is just summation sigma I squared, I from 1 to n. Okay, I get a nice tail bound for this sum of independent random variables of this form, where sigma squared is like that. And then you can play with it a little bit, and the same goes for the lower tail. If I want to look at the average, I can divide both sides of this by 1 over n. So divide here by 1 over n and 1 over n here, and then change t to n times t. You could do a different variable, but let's keep the original variable. If I do that, I get a t here, and then n is squared, t is squared here. And then I move one of the n's here. So let's do it here. So the probability, this is going to be the sample mean, x bar n bigger than or equal to t. I'm changing t to t over n. This would be x to the negative n squared, t squared, 2 sigma squared. I can do this because this holds for any t. I can just reparameterize. And then I move one of the n's downstairs. So you get x negative n t squared over 2. Sigma squared over n, I'm going to call it sigma squared bar. Okay, sigma squared over n is just 1 over n summation sigma I squared, which is like an average variance or average standard, subgaussian standard. Okay, in particular, you get this result. And let's say if all of them have the same subgaussian parameter, this would be that same parameter. You can see the sample mean concentrates the way that you like, e to the negative n. So that it goes down like exponentially fast in n. In other words, it's like sigma bar over root n is how far you have to move. That's the scale that you have to move to, like, so that the probability drops like e to the negative, like t factor. So if I do like t times this, then the probability would be e to the negative t squared over 2. Another way of writing this, if I'm not wrong, you can reparameterize again like this. T bigger than sigma bar over root n is e to the negative t squared over 2. And this is saying that if I move a factor of like 4, this would be e to the negative 16 over 2, e to the negative 8, which is pretty small. So the probability that the mean is like 4 times this value is small. So this tells you the scale of concentration. Okay, questions? So we achieved what we were looking for. If you go back, either this or this is the exact exponential inequality that we wanted. So this was the thing that I wanted. Exactly, you can apply it. This is going to be subgaussian here. And this bound holds except without this 1 over 2. So you get the same bound, but you'd lose the 1 over 2. Okay. Questions? Comments? We pause a little bit. So to summarize, we did the Chernoff bounding and then bounded the MGF or assumed something about the MGF. And then that led to a tail bound. And then we saw that independent sums of subgaussians are subgaussian, you apply the same bound to this sum, and this gives you the kind of concentration that you would hope for sums of independent variables, exponential concentration. Okay. This is also called the Hafting or Hafting inequality, although the original Hafting version is for bounded variables. So if you apply this inequality with xi being each being in ai and bi, and sigma i's would be bi minus ai squared over 2, that would give you the classical Hafting's inequality. So it's a generalization of Hafting's inequality, but it's sometimes called Hafting's inequality still. Okay. Original one only for xi in ai bi almost surely. And then we can apply it with their subgaussian sigma I with sigma I being sigma I squared being basic, or yeah, this being bi. Let's do this. Bi minus ai over 2. So if you do it and then compare with what we get from, just look up Hafting's inequality and you'd get the same. Okay, sounds good. I should point out that for Bernoulli's, you could get a better bound. For this particular case, where you have Bernoulli's, there's a sharper bound, which is which you may see in your homework problems. It's called Kramer's bound, which is it's a large deviation bound, and the KL divergence or entropy is coming. Like there's a rate function which is better than what we have here. So you get e to the negative n times the rate function, and rate function is generally better than t squared. But you'll see this in the homework, hopefully. So there is some generality achieved here, but if you work with the specific random variables, let's say Bernoulli's or binomials or Poissons, there might be better, slightly better bounds. Okay, any questions? Okay, so now here's a bit of a technical slide. This is from the high dimensional book by Roman Vershinin. This is HTP, my notation for abbreviation for that book, proposition 2.52. You can go check, and he shows the equivalent characterization of subgaussianity. So we did this. So we defined subgaussianity when the expectation is 0, like this. So there exists a constant, let's say k5 squared. This was sigma squared for us, such that the MGF is bounded like that. But there are other characterizations in terms of other properties. For example, this is equivalent to this characterization. So we showed one way of it, right? So if I have something like that, then I have a tail bound, two-sided tail bound like this. And this k1 squared is basically related to this k5 up to a constant. So these are like, they're universal constants, like numerical constants, 2 or 5 or 4, such that this is like k5 is bounded by 2 k1, and then k1 is bounded by 1/2. Something like they're the constants, like k1 is c1 k5 and then c2 k5, and these are universal constants. Universal constant means that just they're numbers. Universal. They're numerical constants. So you can see, for example, if we have it with, we have like sigma squared, that's our k5 squared, then the constant there would be like 2 sigma squared, I believe. Does he have a 2 here? It doesn't have a 2, so this would be like, if you imagine this is 2 sigma squared, this is sigma squared, so there's this constant like 1/2 relation between them. in one direction, and the other direction is also true. So if you have this, we haven't shown this. If you have this for all t, then it would imply, if the mean is 0, it would imply this. So you can go look at the proof of that result. The more interesting one is that it's equivalent to this growth of the moments. So if you have a random variable, the LP norm is defined like this. So the expectation of the absolute value to the p to the 1 over p. For example, p is equal to 1. This is just the expected absolute value. If p is equal to 2, this is like root of the second moment, and so on. So these LP norms grow like a constant times root p. Okay, so the moments grow somewhat slowly. Yes. So these are definite. So let's say I take this as a definition, right? So we will say a random variable is subgaussian if there is a constant, which we call it K5, let's say. Constants, yes. Yeah, but the point is that these constants are related to each other up to numerical constants. So if a random variable satisfies this with some K5, then it's going to satisfy this with some K1, which is just a factor of this, like multiple of this, yeah. For us, this was like sigma squared. There's a parameter that we allow here. So the moments are going to scale like this. There's this K2, which again is in sort of equivalent to these other constants by these numerical, like this. And so the thing is that the moments grow like root p, okay? So for example, you can use this to describe how the moments of absolute moments of the sum of a bunch of independent random variables grow as a function of n. I'll hopefully assign as a homework problem. Okay. It's hard to have an intuition if this is good, but this is good. So it grows like slower than what you'd expect. It's hard to convey that, but let's say if you look at the sums of independent random variables, if you sum a bunch of random variables that there's zero mean, the absolute, take the absolute value, take the expectation. So if you do like expectation of that sum to the power p, and then 1 over p, let's say. Oh, okay, that's, yeah. Let's say do this. You might be able to show that this goes like n to the p over 2. Because the subgaussian, well, let's just forget about this. You'll show it in your homework problem, hopefully. So it grows slower than what you would expect. Some of deterministic numbers grow. And that's sort of a manifestation of concentration. So there's another characterization. So this is equivalent. If you can show something like this for a random variable, then the random variable has to be subgaussian. It's generally harder to do this. You can do it for like integer moments, and then argue that because this holds for any fractional number as well, like any real number bigger than or equal to p. But it's enough to do it for integers, or even 2 to the odd integers, or like even integers, and then argue that in between has to like follow. And then the next one is that this is like the MGF. It's a little bit weird way of writing the MGF, but MGF of x squared, basically. Okay, so x here, x squared here, this is bigger. So when you square around the variable, tails become heavier. So it's saying that the MGF of this is sort of bounded in a neighborhood of 0, or actually this one. This, I'm going to skip this. This is almost like equivalent to this. This is saying that if you take the expectation of exponential of this divided by that, this is bounded. 2 is not important. It can be any number. It's convenient to be 2 here. If you look at this, this is just MGF of x squared evaluated at this 1 over k 4 over 2. So there is one point at which the MGF of x squared is finite. So the interesting thing is that this is also equivalent to subgaussianity. So if you can compute the MGF of x squared at a point and it's bounded, then it has to be subgaussian. Okay. I'll leave 3. We're not going to use that. So tails, moments, the MGF of the random variable, and the MGF of the square of the random variable. So these are the interesting characterizations. And a lot of it follows by doing Taylor expansion of the exponential near 0, or inequalities, proper inequalities involving exponentials and such. Questions? So this characterization is used to define a norm on the space of subgaussian random variables. So any random variable is subgaussian if this holds for a certain constant. So if I fix my random variable, I can ask what is the smallest constant that goes there. The smaller I make it, the bigger it gets. So the less likely it's satisfied. So at some point I have to stop. So the smallest that this gets, so I'm calling it here t, the smallest t for which this is less than or equal to 2 is going to be a number associated with that random variable. This is called the psi2 norm, or subgaussian norm of x. And you can actually show that this is in fact a norm. And just an aside, you can do this with any of these constants. So the smallest k that goes there, that's defined a norm as well, which would be equivalent to this norm. The smallest or constant that goes there is going to be another norm, which is equivalent to the other ones by this fact that they're all within constant factors of each other. But this is common. This is one of the established things that people do. And there are some nice properties of this. So, so this is the norm that often people use. And so this, again, this is going to be within a constant factor of that sigma that we define. So if you think about the sigma, sigma squared here, that was sigma squared. This is going to be within a constant factor of that. It's a proper norm in the space of subgaussian random variables. You can go check. It satisfies a triangular inequality, for example. It's homogeneous. So if I rescale something like x by alpha, alpha comes out. You get absolute value times like alpha x psi 2 would be this, and I have the triangular inequality and things like this. So it's a proper norm. Like one step further is actually makes the space into a Banach space, if you like that, like functional analysis. It's like a proper space now. Then you can talk about the convergence and things like this in this norm. So then I can restate all these properties in terms of this norm. So there's going to be a constant times this norm squared here, a constant times that norm. Actually, there's no constant because the norm goes there because this by definition, a constant times that norm, a constant times that norm, and so on. So if you rewrite this, you get these alternative, like equivalent characterization of the subgaussian. Okay. So a subgaussian random variable is a random variable that satisfies this tail bound for some constant c. This constant is a numerical constant. And we often don't care in this course to specify these constants. Okay, and it's just like 1/2, 2, like pi over 3, something like that. But part of like the idea of high-dimensional statistics, part of the culture is that they don't, and high-dimensional probability, these kind of non-asymptotic bonds, is that we often don't care about the actual constants as long as they're universal constants. Okay, if it's a constant that depends on some other things, we do care about it. But if it's a constant that's just numerical, independent of everything else, then this is good enough. So whether there's a 2 here or 10 here or 100, at this point we don't care. Okay, so this holds. That's that other k that we had, which is within a constant factor of this. This goes there without a constant because that's the definition. There's another constant. So these constants are also not exactly the same. that's another part of the culture, that the constants from one line to the next could be different. Okay, so when you read these papers, this constant is not necessarily that C. It's just a placeholder for a universal constant. I could have written everywhere C, but what I mean is every occurrence probably different thing. Okay, if you want to keep track of all these constants, it gets like really hard at some point. So C1, C2, C3, C4, C10, and then at some point you just give up and say, I'm going to write C for everyone. Don't think that they're the same. Okay, so there's nothing new here except some conventions, and the fact there's this fact that these constants are numerical. They're not they don't, for example, depend on the particular random variable that we're looking at. Okay, they don't depend on anything really. So, for example, I can work with this psi2 norm, and I can manipulate random variables, and then once I have a bound on the psi2 norm, I get this tail bound. So instead of the subgaussian parameter, I can just, so this was used to this bound in our previous slide was something like this: negative 2t squared or 2 sigma squared. You can see the constants here are explicit. The sigma squared is subgaussian. This is exactly the same thing, but now the constants are implicit, and then sigma squared is replaced with this, which has more interesting properties, I would say. This could have been a norm, but we didn't define it like a norm. So, questions? This takes a while to get used to, but hopefully by like lecture 10, let's say, you get comfortable manipulating this. So this is just summary of what we mentioned. So if you think of that sigma x, if I look at that subgaussian parameter, it's within a constant factor of this norm. So one way to say that bounded random variables are subgaussian is to say something like this. So x infinity is, this is sometimes called essential supremum. I don't know how to write it, but let's say if you have a random variable, it's like it's a function on the sample space, and so the maximum that it can get modulo a set of measure 0. That's called the essential supremum. It's just an infinity norm. So it's just about, if you think of the random variable as a function, this is just the infinity norm of that function, except that this is defined on a measure space, so you don't care about it could be like, I can change the value at one point to be something really big. I don't care about that. I just want basically the smallest upper bound on it that holds on a set of measure 1. For all intended purposes, you can just ignore the essential supremum. It's just the supremum, the maximum that the random variable can get. So a random variable that's bounded by B, the infinity norm is almost surely the infinity norm is bounded by B. Okay, bounded random variables have bounded infinity norms. So this result is saying that psi2 norm is up to constants controlled by this. So this notation, and again, another part of the culture, this means A is bounded less than or equal to C times B, where C is a universal constant. So this, if I want to unpack this, maybe unpack it here. X psi2. This means that this guy is less than or equal to some numerical constant times x infinity, right? And this we have proven because we have shown that sigma squared, so sigma, that's the subgaussian normal bounded variable, is bounded by b minus a over 2. Actually, this is like this, right? So if x is in a and b, and this is like that. So this is a numerical constant times the, let's say imagine, it makes sense if x is in, let's say negative a and a, okay? Otherwise this bound is not good. So let's say x is bounded. So this is saying that the supremum, our sup norm of this is bounded by a. If this is almost sure, then sigma of x would be bounded by 1/2 a minus a, right, which is just a, right? And this is up to constants bounded. So yeah, that this is bounded by a constant times sigma x. So this is going to be c times a, or c times yeah, okay, so let's say this is equal to this. This didn't quite work the way I want it, but you can take a to be just the smallest. So if this is equal to a, then x clearly is in negative a and a, almost surely, right? So this holds, and then you get this. So this is saying that the psi 2 norm is bounded by this, but this inequality, so I mean, if you go through this, you prove that this is bounded by constant times x infinity. Okay, so this is a compact way of saying that bounded random variables are subgaussian. So the class of bounded random variables have finite infinity norm, and this inequality says that this norm is dominated by that norm. So this class is included in this class whenever you have dominations of norm. So if I have two norms, one is smaller than the other, the ones that have finite this norm would have finite this norm. So this class will be inside this. So this implies that class of bounded random variables is a subset of class of subgaussian. I don't know if I managed to convey that nicely, but the advantage of using norms is like this. So once you establish an inequality of norms, it just tells you something about this classes of random variables, okay? Was it clear? Sort of. It's just a compact. So think about this. This is the compact way of saying that bounded random variables are subgaussian. If you go up, you can see that, for example, from this, the L2 is bounded by C times the C primes times psi 2, right? Remember, this is this equation. I've written it in terms of the norm. So this implies that whenever this side is finite, this side is finite. So like the psi 2 class is a subset of the L2 class. So some Gaussian variables are in L2, but you already know that. So part of this result is that because this is a finite constant, all these moments are finite. Okay, so that's part of the point that was mentioned. So because we have the finite MGF, all the moments are finite. So sub-Gaussian class is within the LP class for all P. Okay, so sub-Gaussian class is in LP for all P. So this is like the functional analytic version, and this is like L infinity is inside this. L infinity is all bounded random variables. So bounded random variables are in sub-Gaussian random variables, and these are in LP for all P. Okay, so that's the nestedness. So they're bigger than these, but smaller than any LP. Sounds good? This was a little bit abstract, but once you think about norms, you can think about the spaces, and once you think about the spaces, you can think about how they're nested, and this gives a nice picture. So like the relative like location of this class, which is not too small, not as small as L infinity, but not large because it's just inside all the LPs. So LPs, do you know how these spaces themselves are like nested? So L2 versus L3 versus L4. Anyone knows how these guys are? So L1 is the set of random variables that have finite first moment. L2 is a set of random variables that have finite second moments, and so on. Okay. Yeah.
The higher speed finite applies to the lower.
Yes, exactly. For in probability spaces, if you have higher moments, all the lower moments exist. So LP is going to be inside LQ if P is bigger than or equal to Q. For example, L2 is inside L1, and then L3 is inside L2. So it gets smaller. Did I write it correctly? P bigger than Q. Yeah, the higher the moments, the smaller the class is. Okay, this is not true in general measure spaces. So that's in Rn. If you have the Lebesgue measure, they're not nested. So L1 and L2 are not nested. There's an intersection. But in the probability space, they're nested. So what this is saying is, okay, maybe I should clear this out. Cut. Should we do this? Okay, I'm going to do it here. So LPs are like that, L4. And so the picture is like this, L infinity, and then subgaussians. And then this is inside all the L's, or LPs, like up to like, they go this way. So L3, L2, L1. So it gets smaller and smaller, like infinitely smaller, and then you hit the subgaussian, and then you hit L infinity. Okay, so they're much bigger classes. So Cauchy, for example, is in this, but not in this. There are random variables that are in this, but not in this, and so on. Okay, so it's a fairly small class, but it's still bigger than L infinity. What happened to L1? And then this is inside all measurable, like, I don't know, M. There are even random variables that are not in L1. They don't have any moments. So okay. That was like an excursion into functional analysis. So back, any questions? This wasn't that needed, but it's just a nice way of stating that subgaussians have moments of all order. Okay, that's a nice way of saying it. There's this result that if you center, so if you have a subgaussian variable, we know that this is, actually, this is the result. The centered version is also subgaussian. That's part of the way that we define things. But the subgaussian norm of this is going to be bounded by constant, universal constant times the subgaussian norm of psi. That's helpful sometimes because you can get rid of a centering. But if you have a bound on the subgaussian norm of this, the centered version at least guaranteed to be as large, the norm up to a constant. And the proof follows from the fact that this is a norm. So this is going to be, this thing is going to be bounded by subgaussian norm of x plus the subgaussian norm of this constant, if I call this, okay, let's do it properly somewhere else. How can I do it? Okay, just let me do it here. So this is going to be bounded by psi2 plus, it's a norm, so psi2 of this guy. But this is a constant variable. Okay, it's bounded by the infinity norm, this part. So this part itself. is bounded up to a constant by the infinity order, just the size of it, which is just this, right? That's this inequality that we mentioned here. And then this is bounded by, this is Jensen's inequality, right? And this is the L1 norm of the random variable, right? And L1 norm, like all the norms are bounded by the psi2 norm. So the L1 norm in particular is bounded by another constant. So this is bounded by C prime times the psi2. So if you put back together all this, the whole thing is bounded by the psi2 norm. It's a good exercise to see how the fact that this is a norm and how the fact that these inequalities work help you just simplify and then get a bound like this. So I would encourage you to go through the proof of this. It's also in the HTTP book. But this is the short proof here. If it's not clear, try to do it yourself and consult that book. But this is an example where these techniques are coming. Okay? We're almost out of time, right? So just one comment is that this is a good bound, usually for like single random variables. But if you want to try to apply it to, let's say, Sn, which is the sum of random variables, usually this side is much smaller than this. Because this bound that we had here is like bounding the expectation here. The thing is that the deviation of something from this expectation is usually smaller. And if this expectation itself is very big, you're basically bounding this by the psi2 norm, whereas it's like this term could be much bigger than the psi2 norm of the deviation. Okay, so the size of the expectation is usually much bigger than the subgaussian sort of concentration parameter. So just be careful that this is sometimes good, but you have to know where to use it. Okay, it's not always good. Okay, one final thing before we move on. You can restate everything that we did before in terms of this norm. So for example, if I have a bunch of independent zero means subgaussian random variables, the sum is subgaussian, and the subgaussian norm is squared is up to constant sum of the subgaussian norms squared. This is like saying sigma squared is less than or equal to summation sigma I squared, but then I have to pay a constant here because for that there was equality, but each one of the two sizes are like up to constants in correspondence with the norm, so I get the constant here. So that's a restatement of that fact and restatement of the Hofstine in terms of this. There's a 2 there. Instead of sigma I squared, you get this. This is very useful because then you could just play with the norms, psi2 norms, and use the properties of the norms. You don't have to worry about much else. Okay, that's it. And next time we come in and go to a larger class, which are sub-exponential class. Okay, thank you guys. Have a good weekend. See you next week.